So in this video, we'll be looking at Ampere's law for ribbon cables and sheets. This is no longer a cylindrical symmetry situation, so we have to use a slightly different choice of Amperean loop. Other than that, the details are going to be about the same. The specification of this ribbon cable is we have N wires per meter. And the specification for the sheet of current is that we have a current density J that is only a function of Z, where Z is measured from the middle. And furthermore, it's only a function of mod Z, which means that it does not depend on the direction, whether you're above the sheet or below the sheet. So it carries a symmetric profile. The simplest case, of course, would be a constant current density, but it also allows you to have some variation in the Z direction, provided that variation is the same above and below the center line. So we're going to take the Z coordinate to be measured from the center line and the minus Z coordinate to be measured from the center line below. So here the coordinate system is going to be X, Y outside the plane and Z axis up and down. So I'll indicate that by writing the X axis here and the Y axis to be out of the plane and the Z axis to be up. Over here, the ribbon cable has the same kind of structure of the coordinate system, so I won't bother repeating the coordinate system here. Let's do the ribbon cable first. Now at first blush, we don't know if the magnetic field changes with Z. So just to preclude any possibility of changing with Z, we'll take the Gaussian pillbox approach and take an Amperean loop that is equal in both plus Z and minus Z. Now from your right hand rule, you know that if current goes into the page, by your Biot-Savart thumb right hand rule, if current goes into the page, then the magnetic field is going to be given by your fingers. So we know that the magnetic field is roughly going to look like that. Okay, that's our expectation. So we are going to take the orientation of this Amperean loop to also be like that. And then when you come down here, we know the magnetic field is going to be something like this. So that is nice to have as the orientation. Now I notice that the orientation is clockwise. I chose it to be clockwise here because I know the magnetic field is also going to be clockwise. So depending on your orientation, you have to be clever to choose your magnetic field or direction. You have to be clever in choosing your orientation. Now I do not know yet if there are going to be magnetic fields on the sides. If there are, it's presumably going to be bigger as you get closer. So I'll draw some bigger fields here. Okay. And over here, I'll draw bigger fields in the opposite direction. Now for the ds vectors. The ds vectors are faithfully going to follow the loop's direction. So there the ds vector is going to be along the loop. I'll draw them with this darker ink. So one feature of the ds vector you notice immediately is that the ds vector is perpendicular to all these side magnetic fields. So the contribution is going to be 0 when we take the dot product, which is as well because we don't know if it's there or not. It turns out not to be there, but we'll see that miracle occur shortly. So the left hand side of Ampere's law, let's first of all write what it is. Ampere's law tells us that the magnetic field dot ds is mu naught times I enclosed. We're going to apply that to this and then to that. Let's work on the ribbon first. The left hand side of Ampere's law here gives us several terms. So the integral of B dot ds along the curve C is going to be the integral. Now it's no longer a closed curve. I'll do the top surface, top line, not surface. And this is B dot, be careful, the coordinate system, that's dx. So that's B dx, and since B and dx are in the same direction, it's B dx cosine 0. And here at the sides, right side, it's going to be B, let's be careful here, it's dz cosine 9t. And then it comes here back, so there it's bottom, B dx cosine 0 again, and then to the left side next, and that's dz, cosine of 90 degrees. Well, now cosine of 90 is 0, so these two terms just vanish and you just have those two terms. Now by symmetry, because I have taken the z value of the loop to be the same above and below, the magnetic field is going to be the same, even if it depends on z. So let's write this as b of z times the integral of dx. Now the integral of dx is just the length of the loop that we chose to have. So let's put a length to that loop times L. And I'll have another term from that that looks exactly like that. So it's just 2bz times L. And that's the left hand side of the ribbon cable. The right hand side of the ribbon cable is the current enclosed. I've told you there are n wires per meter, so the current enclosed is just the number of wires, which is n wires per meter times L, times the current in each wire, which is, let's call it capital I. So I get, therefore, 2b of z times L is equal to mu naught times the current enclosed, which is n wires per meter times the length, that will give you the total number of wires, times the current in each wire, which I'll call I. Observe now, L cancels, as it should, because L is a figment of your imagination. It doesn't really exist. Ampere loops don't exist. So mu naught is a constant, n is a given to you, I is given to you, so I have b of z. And what's more, I find that b of z is not a function of z at all. So in this way, the realization dawns on me that it's constant throughout. And that's another remarkable result. If you have a true ribbon cable that's infinite, then the magnetic field will not decrease with distance. And you can again rationalize this in the same way as you rationalized why the electric field does not decrease with distance from an infinite sheet of charge. As you go further and further out from the sheet of charge, you get more and more of the charge in view. So the fact that you're going farther away and you have this 1 over r squared effect from each charge is exactly compensated for by the fact that you're seeing more and more charge. And r squared's worth more. So in the same way, here also the same thing. If you have a certain field of view, you're only going to see a certain number of wires. But if you increase your field of view, you're going to see more wires, but you'll also be increasing the distance. So those two things will compensate. This is the magnetic field of a ribbon cable, and the magnetic field of a solenoid is just twice this. So you can use the superposition principle as I show in my notes, and magnetic field of solenoid, B sol, it's a very famous magnetic field, so I'll write it here, is just mu naught Ni. So those are the magnetic fields for a ribbon cable and a solenoid. Let's now deal with this slightly more troublesome cousin, and that's an infinite sheet. But it's not truly troublesome. It just means that you have to look at two separate Amperian loops, one inside and one outside. And here I'll take one Amperian loop, which I'll call C1 inside. Now notice the direction of current, I've purposely taken it to be inside here and outside there, just to give you some variety. The current direction is outside, so a magnetic field is going to be in this way. It's better to take the loop to be oriented like that. Once you have that, then B and ds are going to be in the same direction. The left hand side is going to work out exactly like that. I will not bother doing it. I'll just get 2 times B of z, that's also L, times L equals, and now this is where you have to be a little careful. It's mu naught times the current enclosed by this loop. Now this loop has got a current density, so we have to take the double integral of J as a function of mod Z times the area, and the area is just dx dz. You'll observe that this J of Z does not depend on x, so the integral over x can immediately be done. So that's just going to be mu naught L, and the integral from negative, let's put a dimension on this too, Let's call this W. Actually, let's call this W equal to 2z because it's z above and z below. So it's going to be integral, well, since it's even, it's 2 times integral 0 to z, j of z without the absolute value sign, dz. And you're done. I can throw as complicated a function as I want for j of z because this is just a one-dimensional calculus problem. You can either do it by yourself using the techniques of integration or stick it into Wolfram alpha, I don't care. And once you do that, you have b as a function of z, all done. What about outside? We still have to worry about what the magnetic field is outside. So take a bigger Ampere loop, the cousin of this one, and I will leave it as an exercise for you to write these terms. It's going to be integral b dot dx there, and then this part's going to be 90. That's going to be 90 inside the metal, and then it's going to be 90 below, and then it's going to be outside again 90 degrees, and then it's again b dot ds or b dx here, cosine 0, outside, inside 90, inside 90, outside 90. So you can write all that. It'll have about let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 integral terms. It's fun to write those integrals because most of them will be 0, but the end result will still be this. So this is for Amperian loop C1. Let's call these C1 and C2. For Amperian loop C2, I'll get 2 times b of z times L equals mu naught. The only difference between this and that is I go to the entire width. So let's call this now the width of the wire to be 2 times the thickness. I'll call the width of the wire to be 2t. So mu naught L integral 0 to t j of z dz. And you're done. Observe that this integral will not depend on z. Here it does depend on z. Here it does not depend on z. So if you try to draw the field profile here, it's going to look interesting. So let's take a moment to draw a field profile. Since I've not told you what j of z is, I cannot obviously be very honest about this. So bt as a function of z. Actually, it's not tangential anymore. It's b in the direction of the b has got x component, so it's going to be bx as a function of z, not bt. Let's take positive x to be up and negative to be down, negative values of in the x direction to be down. So you'll see that the magnetic field here is in the negative x direction in the top, then here it's 0, and then here it's going to be in the positive x direction. So let's go from z equals negative t to 0 to positive t, of course to infinity and minus infinity here. So when the z values are negative, the magnetic field is positive. So I have to be a little careful here. And it's going to be the opposite here. So as long as I have those two written down, I don't care what the middle looks like. Now I've not told you what j of z is, so it may be something crazy. I'll just draw something like this. Whatever it is, it needs to be symmetric. And once you come to the t value, you're frozen at that value. So the magnetic field will continue to be constant forever.